Again, thank you everyone for coming. This is Cost-Conscious Tolerancing of Optical Systems. I will be repeating my contact information at the end of this webinar. Just really want to encourage people to reach out to me if you have additional questions. Here's an agenda. I'll first talk about who this presentation is for. Then I'll talk about what an error budget is. I will be talking about error budgets for the next 40 minutes. You have expected to come here and hear about tolerances, but just know that an error budget is a structure, a discipline that is used to generate tolerances. I'll talk about when error budgets should be used, what the benefit of using error budgets are, benefits. Finally, I'll go through the 10 steps of creating and using error budgets. I'll then have just one chart on cost-saving tips. So what I do in this short course is go through the 10 steps of creating and using error budgets. And wherever cost-saving ideas come up, I have a little green $ on that chart somewhere. Then at the very end of the course, I summarize all those cost-saving tips in one area. So I'm just going to show you at the end of today some select cost-saving tips that come from that course. And then finally, we'll do the summary and you'll be able to ask questions. So first of all, who is this presentation for? First and foremost are the folks that I've got listed here. So obviously lens designers. Lens designers are the ones who develop the prescription for our optical system. So shapes, materials, positions of lenses and mirrors and things like that. The course is also for the whole array of different kinds of engineers that work on a project, such as you see on the right here. So optical, mechanical, structural, thermal, manufacturing, could be electrical, so forth. And then finally, systems engineers. Probably half of you are quite familiar with what a systems engineer is. Maybe some of you aren't so much. It's something I talk about in detail in the course. But the systems engineer is really the perfect person to create and maintain an error budget from which tolerances flow. So that full day course is ideal for all these types of folks. Also, it's possible that people from optical fabrication would want or are interested in where do the tolerances come from? Why am I stuck with this tiny shape error for this one mirror, this one lens? Folks who work in metrology, both optical element metrology, surface metrology, all the way up to system level testing. Again, they're going to get allocations. They're going to get tolerances that come from these error budgets. And then finally, team leaders and managers might also be interested. The process that I'm going to talk about here is pretty involved, takes resources. And so those leading these groups would be interested to know what are the benefits of providing that resource. So what is an error budget? Well, it's a method of managing one or more performance metrics. And in an optical system, a performance metric could be something like wavefront error, modulation transfer function. It could be something like distortion or another aberration that we're trying to minimize. Those are just a few examples. An error budget involves breaking down a total error allocation and assigning it to parts of its various components. It can be assigning them to different disciplines, or it can be assigning parts of that error to different stages of design and development. So here's a very, very simple budget that you've all probably seen. You can tell how long ago it was that I made this budget because a monthly income was $3,500 at the time. I've been around a little bit. But this is just a financial budget in which we take a total error allocation, or let's say a total amount of money for each month, and we break that down to categories. And then we break that down into subcategories. One thing you'll notice is that I always have a box over to the right here for margin. And in the same way, you'd want to have maybe some extra emergency money in your monthly household budget. We want to have some margin for errors that contribute to performance in our optical system. So all of the budgets that I use in the course, the technical budgets actually look like this, literally with the colors and boxes. Now, these budgets can be used top down or bottom up. So I just discussed a top down, saying we have so much money, we have so much allocation for something, and I'm flowing those numbers down to the subcategories. They can also be used bottoms up, which means if we know exactly what our co-pays are going to be, or exactly how much we're going to spend on food each month, we can fill in the lower level boxes and then add everything up to the top and see how much do we need for each month. Here is, please don't get too excited about this very, very fine print, but this is an example of an actual error budget for an optical system. It's actually a pretty simple one. And it is for, I'll show you up in the top here. This is our top level error that we are assigned. So it's actually for a focal length. It is actually, those of you who have worked on optical systems for a while, it's not common to see a focal length error budget. However, I use this in the course and we go through this in detail because it is a pretty straightforward exercise. Later in the course, I get into more complicated budgets, such as geolocation, modulation transfer function, etc. But the focal length budget is pretty straightforward because it doesn't involve that many elements that you see below. Even though this looks like a lot, they get bigger. And the sensitivities are linear as well. So just at a very, very high glance, you'll see that I've broken the focal length errors into 5 different categories. And then I've broken down into subcategories and then sub-subcategories. And it's in this chart that I keep track of everything that can affect focal length, all the way from the beginning of design to our fabrication of elements. Then we put the system together. So we assemble the components and align everything. And then after that, we have operational errors. So shipping loads, possibly gravity release, thermal things that happen, dynamic things that happen. And then finally, we're going to keep some margin in our budget. So this is just a glance at what an error budget might visually look like. Okay, now why should we do this? When should we do this? So one argument about using error budgets is that they should always be used. We always need to find some kind of way to organize how the different parts of the system contribute to errors in our performance metrics. Another possibility is when required by a customer. So many, many decades ago, I worked for a customer that required the use of error budgets and in fact visited on a periodic basis to find out, what does your error budget look like? So over time, things change around and the customer can pop in and sort of see, where are you in trying to meet this budget? Imaging systems, and here what I mean is, in contrast with illumination systems, I've used error budgets, this formal system, much more often for imaging systems than for illumination systems. Probably obviously for diffraction limited systems, you can't really have any errors of any magnitude at all. So you've got to keep track of each and every one of them. Some special kinds of systems, those with large or lightweighted components, shape errors that we get in those optics really explode this procedure. There's going to be a lot more elements in this procedure. Same thing with systems with numerous components or functions. So if you think of an image chain analysis, everything that goes on from end to end is going to be involved. And again, a system to keep track of all of that is really important. And then finally, systems with significant environmental challenges. I've worked on many projects for which we only really look at the fabrication and alignment. People just sort of forget what's going to happen when this product is out in the real world being used in some environment. In a lot of senses, that's fair. But when those environments are challenging, we need to put a lot more work into that part of the equation, that right-hand side of that budget tree that I showed you. Okay, now error budgets should also be used when an appropriate engineer or a systems engineer is available. In my course, I talk about there's sort of a list of skills or personality types of appropriate engineers. And I'll just give you a hint, it helps to have an anxiety disorder or two. So that person who's juggling all these numbers needs to be very, very conscientious and have other types of personality traits. Just to mention, I also have a master's degree in psychology. And so in my course, I do talk about things like the personality types of people in different roles and other behavioral types of advice for going through this process, making sure we're communicating and coming out with the best possibly toleranced optical system. So the benefits of using the error budget, I've alluded to several of these so far, but in this process, documentation is created that assures customers and your peers that requirements are being well thought through. The work is performed at a system level with multidisciplinary visibility. So back in the day, we thought about how a lens designer would do their job first. They would finish up their design. They would then use their optical design software to create tolerances. And then they were sort of the ones to carry that error budget throughout the project. It's not really fair. Lens designers don't always have the skills that are needed to handle the error budgets, or they're designing 42 different designs at once. So if we do this at a higher level, at a multidisciplinary level, with a systems engineer, ideally, then the lens designer can do their part, move on to something else. But also this exercise can be started before the lens design is done. So those two folks can be working in parallel, and we can be thinking ahead to other parts of the system, not just waiting for the lens design to be complete. The use of an error budget allows the whole team to visualize error allocations, identify missing allocations, and make good suggestions. So when I say visual, I will actually take that big chart and chart it out on a plotter and put it on the hallway outside my office so people can come see. The use of the error budget also gives you a framework for juggling allocations, switching tolerances around all through the design, development, and even after the products have been sold and are out on the market. It also gives us a framework within to troubleshoot. And a framework for your next project, so you're not starting off from scratch. Now, here's one of those dollar signs that I use in the course. Just want to mention, hopefully this is already obvious to you, that creating and using error budgets is a cost-conscious activity. So here are the steps. These 10 steps are my 10 steps. And I'm not going to read through these right now. I've got a chart on each one of these. But I want you to know that these steps are like the stages of grief. You do not need to go through them in order. You are welcome to skip steps, and you are welcome to circle back and repeat steps. And specifically, if that's not happening, that circling back, you could probably be doing a much better job. So it's expected to skip, it's expected to skip back and repeat. So this development of an optical system that meets all of its requirements, it is a living organism. So number one is quite simple, but it's to fully define the performance requirement in writing. If we have a wavefront error requirement, let's say we want to define, is it peak to valley? Is it RMS? What field points do we need to be concerned about? In what environments do we need to be meeting this wavefront error, and et cetera. And I like to tell people, get that in writing and actually have someone sign it. Let's make sure that before we embark on this process, we've got the right requirement. Now, the second thing to do is to select an organization for your error budget. So here's the generic error budget look. And we can arrange this in many different ways, and it almost wholly depends on what kind of system we're talking about. If it's a space telescope, you may approach it one way. If it's a spectrometer, you may approach it another way. And you'll know as you start to think about how to organize it. So one way to organize it is by discipline. So we have mechanical stuff going on. We have electrical stuff going on. Here we just simply go through our system from the first optical element to the last optical element and just say, what is everything that can go wrong with lens 1? What is everything that can go wrong with lens 2, and et cetera. Another one is, what are the types of errors that contribute to our performance metric? So let's say modulation transfer function. If you have radius of curvature errors in your optics, maybe we could lump those all in that category. We have irregularity on the surfaces of all of our optical components, etc. Now, the one that I've shown you today is the one that I most often use, and it's really sort of a chronological organization. We start with any residual design errors. Then we add in the errors that come from fabricating the components. And then we bring in assembly, alignment, and then test of the system in, the full system before we sell it off. And then we bring in the operational errors that come after that. So fluctuating temperature, for example. Now, this chronological organization lends itself to testing at 2 or 3 different levels. So when we do this chronologically, as we test things, as we test subsystems and bring in more, that gives us a chance to compare the predictions that we made up to that point to the actual measurements. So number 3, assign starting tolerances for everything that can go wrong. So being kind of an anxious person, I'm really good at thinking of everything that can go wrong. Okay, so some advice on where do we get starting tolerances. This is a real big factor. I encourage people to find people who have done this before and just ask them questions. And you'll want to ask a lot of people. And what you'll find is we've got some optimists out there and we've got some pessimists out there. So the guy that always says, oh, sure, we can do that. We can stabilize that to 2 nanometers. And then you'll run into people who say, oh, forget it. Don't even start. It'll never work. Sure, we've all heard these people. So talk to lots of people and see if you can find a balance that feels right somewhere in the middle there. We can call companies who are going to make components for us. We can read their websites. There's a lot of other resources. There's a lot of papers about this, about what are reasonable starting tolerances. Is it easy to make a lens with a thickness that is accurate to 10 microns or 100 microns, those kinds of things. There's a lot of resources out there. This systems engineer can also start by just doing some back of the envelope calculations. So one thing to think about is considering material properties. If you know your system's going to have a certain length and you know the CTE of stainless steel, you can do some quick checks to see what some reasonable tolerances might be. Another thing to look at is the measurement uncertainties of available metrology methods. So again, let's choose something else. You want to measure the radius of curvature of a mirror. Well, certainly the tolerance that you put in your budget should not be tighter than the ability of the industry to measure that, that parameter. So looking at metrology measurement uncertainty can help you figure out if you're in the right ballpark. And then again, I want to stress this word, everything. I actually have a checklist that I use personally. Again, this is just my list. But sometimes when I sit down and I think about what are all the things that could go wrong in this optical system, I consult this list and I think about Would my performance metric be affected by coding degradation? Would my performance metric be affected by dynamic disturbances in my system or detector resolution? You get the idea. So I just keep this so I can scan through it, make sure I'm not missing anything. Now, step 3, this is another big one. Here we're going to develop sensitivities. And the question for each sensitivity is, how much does each tolerance or each error that we find as we pick through the system here, how much does each tolerance affect the performance metric? So here we'll use our lens design software to get sensitivities, and we will go to the lens designer probably and ask them to develop a set of sensitivities for us to fill in that big chart of numbers. And we'll ask them to do that with and without compensation. So there's always going to be more, possibly more than one sensitivity. So here's an example. Let's say that we know that this radius on the front lens here an error in that radius will affect our focal length. So here the sensitivity is, we're going to find out what is the change in the focal length per unit or per millimeter, let's say, of error in the radius of curvature of surface 1. And our optical design program will tell us that it's going to change the focal length by 0.31 millimeters for every millimeter of error in that radius. That is the uncompensated sensitivity. Now, for this case, I'm going to say we know that we're going to compensate for focus error by moving the focal plane in the axial direction once we've put our lens together, okay? That's going to compensate for focus error, but that's not going to change the focal length, okay? So we don't have any other sensitivities here for that radius. But another example would be, let's say that we have decided that, boy, do we take a big hit when we have an error in the center thickness of lens 6. We have a 1/10 of a millimeter change in our focal length. So we might concoct a compensation where we say, well, we will move this last element axially as we put the system together to compensate for that error. So we're going to want a sensitivity for that. And that does take out most of the focal length error. So sensitivities can be linear or nonlinear. By far, they are linear, even for things that you may not think, like an RMS wavefront error, they're linear. And obviously for focal length, they are linear. Okay, so we have our uncompensated sensitivities, and then we have some sensitivities calculated out. And now what we're going to do is fill up our table with those numbers. So let me just show you where we are right now. I've just taken the fabrication errors part of the error budget, and you can see that the errors in radius for a 6-element lens, now we're going to have 12 surfaces. Those are laid out here. I filled that up with my fabrication tolerances, those starting tolerances that I think are probably achievable. And then what I'm going to do is type in all those sensitivities that I just derived. Same thing for the errors in the center thicknesses of each of my 6 lenses, and then same things for refractive index errors on each of my 6 lenses. So we have a very simple 6-lens camera lens. There we go. Okay, so the first thing we're going to do is multiply the tolerances that we chose by the sensitivities that we just derived. And what that's going to give us is the effect of that error on our performance metric, in this case, our focal length error. So here we're going to get, we're just going to fill out this whole column, and we're going to get the overall effect of each error on the performance metric. We can immediately find our worst offenders. This 0.021 jumps out at us, and other things are not going to jump out at us. And what we can start doing right now is to do some juggling. So maybe to make this tolerance a little bit smaller so that our overall effect on focal length error goes down. We could probably double or triple or increase by an order of magnitude this second tolerance, because it really has very little impact on our focal length. etc. Now, the most important thing here is that now we have this, all of these numbers laid out, and you can use these for the next month, for the next 6 months, for the next 2 years. You can start exercising your what ifs. So if Charlie comes to you and says, you know what, we can't get the vendor to agree to a 50 micron tolerance, you can double that and you can immediately see what the effect on this performance metric is. So it's quite a good investment. Now, this is the part that I call the show the beautiful people. So all these beautiful people come to the table, so to speak, and you're going to show them this chart of numbers, the whole chart of numbers. So we don't just go to the optical fabrication people and say, here are your tolerances, and walk away. We want everyone in all the disciplines to be able to see all of the value, all of the numbers that are up there. So this transparency fosters trust and great ideas. Your team will trust the systems engineer when those numbers are out there for everyone to see. And there's going to be a lot of talk back and forth. So why did Charlie get 10 microns, but I only got 2 microns? That's really good. That's a really good question. People will step in to help each other out. People will pop up with ideas. Well, why don't you try this? Why don't you try this method? You're going to want to be sure that when you show these numbers, that the lead engineers have the inputs that they need. So they need to know, what does the lens design look like? What is the full definition of this requirement that we're trying to meet, this focal length tolerance? What does it include? What does it not include? And then they'll need to know, and obviously these will change throughout the development of the product, but what are the interfaces? So what kind of structures are we talking about? What kind of environment are we going to be subject to? What are our assembly plans? Those kinds of things. And at this point, when everyone's had a chance to look at these numbers, we're going to ask each person, each team, do you need more? Do you need those tolerances opened up? Or can you do better? Because if you can do better, you can save the day and we can give more allocation to someone else. And this first whole sort of populated view can be really useful to find out where the real hurt points are. And so management can be pulled in early to address major issues. So we don't want to go to management right off the bat and say, there's no way we can design a thermal control system that's going to work. Okay. We want to lay all the numbers out, have a multidisciplinary look at things, and the management will be more apt to really spring into action when we can visually present what we're seeing. So step seven is where we get into a little more of a realistic look at our design. So what we're going to do is we're going to start replacing all these little tiny error allocations with groupings that come from analytical predictions. So people are going to start to do some modeling now. We've gotten to a point in our design that we can build structural models and thermal models and so forth. So at the very beginning, the designers, let's say the designers that are looking at how to ship this product, they need some positional tolerances to begin with. So here we have all 6 of our lenses. They're allowed to shift axially by a certain amount when we ship. Or let's say when we launch, there's launch loads, and we have gravity release. It's good for them to have individual physical tolerances to start with, 10 microns, 75 microns. But in reality, what we want to know is, how do all of these elements work together when they undergo this shift? So that analytical modeling will be more realistic, and it can also demonstrate the interactions that happen between these 6 different lenses. So this is easy to do. When sensitivities are linear, we can actually just use those sensitivities to create an equation, and we will give those equations with signs to the analysts. So it will be the focal length change is equal to the shift in lens 1 with a sign giving direction times some coefficient that represents that sensitivity. And now the analysts can figure out themselves, what is the overall change in focal length? They don't have to report back to the lens designer. So I mean, I remember back in the days when people would come to me with a floppy disk, a 3.5-inch floppy disk, and say, here's all the output from my model. And I would go into my optical design model, make all the shifts and shape changes, and then I could figure out what the change in the focal length was. But when things are linear, the analysts can do that themselves. That gives them freedom to let go of some of these very specific tolerances. What matters most is that they're meeting a higher level requirement. And at this point, we can start collapsing these budget sections. And what's going to be left in those sections of the budget are, instead of 18 numbers here, we will have 2 numbers. The first one will be the predicted change in the performance metric. So the analyst thinks there's going to be a 0.1 millimeter change in the focal length. That is a bias. But we also need one more value, which is the uncertainty in this prediction. And that would come from things like inability to perfectly model material properties in our simulations and so forth. So now we're collapsing these sections of the budget down to predictions with prediction uncertainties. Okay, step 8. Now here's a place where I guess a lot of people are nervous about statistics. So I show these scary looking equations. I don't know about you guys, but those are scary to me. However, doing statistics for error budgets is not scary to me. So at this point, this is step 8 out of 10, and this is going to be the first time that we come up with a top level estimate. So far, we've filled out a lot of numbers in the bottom parts of our budget tree. This is the first time we're going to flow everything up, combine everything statistically to see what we're likely to achieve at that top level. Okay. Now, as I said before, you don't have to go through these steps in order. You may have done this already, and that makes a lot of sense. So in the course, I talk about dividing up all of our errors into 2 categories. One is the systematic or the bias errors with sign. We think the focal length is going to increase by this much, or we think it's going to decrease by this much. And then we also have our random or stochastic errors. So those are, I had just mentioned the uncertainty in the modeling, the results that we got from our modeling. Those are stochastic errors. Errors like the center thickness of each lens, those are going to be random in the sense that for any system that we put together, there's a distribution of possible CT values or tolerances. So in a very general sense, if everything in our budget meets the requirements of a normal distribution, our statistics involve nothing but root sum squaring or RSSing all of these values together up to the top. Very quick, very easy. I use that a lot. But again, there are a few very, very important rules that come with that luxury of RSSing. There are other kinds of distributions that are not normal. There are some very classic ones that come specifically with optical fabrication of lenses and mirrors. They are not normally distributed distributions. So we talk about what are some of those other distributions, and then how do we do the statistics when those are not normal. And then finally, we talk about Monte Carlo simulations. A lot of people ask me when I talk about creating error budgets and developing tolerances, they say, well, why don't you just Monte Carlo? And my answer to that is yes. You should create an error budget and you should use Monte Carlo simulations. Most optical programs have them. They're pretty easy to run. And what we do with those is we should be able to show that a Monte Carlo simulation puts us in the right ballpark in terms of meeting our overall top level requirement as our error budget. So we really should be coming up with the same thing. And when we don't, that tells us that we need to dig and we need to look and we need to consider our distributions, what we thought they were, etc. So in the end, what we really want to see for any of these top level requirements is a plot that looks something like this. So across the bottom, I have different focal lengths. And this black dotted line is the nominal focal length. So we're designing a 70 millimeter camera lens here. This band represents the range of acceptable focal length. So this is our 70 millimeters plus or minus the 0.7 millimeter 1% tolerance that we're trying to meet. So anything between here and here is going to be acceptable. But what we did was we built this error budget tree. We defined a bunch of tolerances. We combined them all together using different statistical methods and or the Monte Carlo simulation. And what we find is a distribution that looks like this. So we actually have a big bias in the predicted focal length. On average, we predict this focal length is going to be 70.46 millimeters, which was within the acceptable bounds, and we're good to go. But there's a distribution associated with that. Because every time we go into that Monte Carlo, we choose different tolerances from choose different values for within the tolerance distributions that we've defined. And so what we show here is that this turns out to be 83% of all of these lenses made will be within the acceptable focal length bounds. So you could say 83% of them, or you could say for any given lens, there's an 83% chance that its focal length will be within specification. Okay, step 9, I call this the 3 C's. So these are considerations you may have known you needed from the start. If you have a spectrometer in your system, you probably already know that you need to perform a calibration, maybe once and maybe periodically. If you're going to put together a complicated system, and maybe you've done this before, maybe you know you're going to have to use some compensating activities as you build your system up. Or also, you may know that you need to make periodic corrections in your optical system. So maybe you have to move that secondary mirror in a telescope every time, every orbit, or every time your thermal situation changes, something like that. So you may already know that you need to do these things, or you may have just floated up all your numbers to your top level and found that your budget isn't balancing. And you say to yourself, well, gee, maybe we should make some periodic corrections, or maybe we can implement more compensations when we build the system, etc. So in the course, we learn how to book in our budget, the error that accrues, before we calibrate or before we correct, and then the error in the correction itself. So a lot of times I hear the term, people say, oh, don't worry, it's calibrated, or don't worry, it gets compensated out, or don't worry, we'll correct it later. But we always have to leave behind in our error budget the error in making that correction or compensation or calibration. So we don't just fix things. We still have to book those numbers. Okay, now our last step is simply to continue to keep going through these 10 steps all the way through design and development, manufacturing, testing, and even further. These things are out the door. We want to keep working our budget. We want to try to keep taking cost out of it. So you'll want to keep a revision history, because this budget's going to keep changing as we learn more and more and do analyses. We're going to want to compare measured performance to the predictions that we made once we've got our first few prototypes. So at the point right about here, we will have built our first system. We can do the math to combine all these errors and predict how far off of focal length we are. So when we do put those prototypes together and measure that focal length, and we compare those, does it seem right? And if it doesn't seem right, we're going to need to gather up all of the element data and take a look at it and see where did things go wrong. And at this point, we can update our tolerances. And then there are several resources that talk about this idea of squeezing out cost. So maybe we have met our performance metric, but we still want to be taking cost out. So now that we've got our final tolerances set up, we can go back in and look at those numbers again in the beginning and see if there's anything in there that's generating a zero change in focal length. And if so, let's take cost out of the tolerance, loosen that tolerance, and take out cost because it's not affecting us. So we're always sort of pushing down and letting up until we get the right balance for cost. Now, at this point on step 10, you can also ask customer for relief in that specification or other kinds of changes, maybe in the environment or higher level things that we don't have control over. And at this point, we're in a really good position to make that ask. We can show that big table of numbers and they will realize that we have done everything that we could to squeeze everything out. So we're probably more likely to get relief. And we can also continue using this structure that we've made for troubleshooting. What if this, what if that? And we can also address unexpected changes throughout product manufacturing and beyond. So one example is, let's say that the lens number 2 that we were buying from a certain lens, maybe from a catalog, is no longer available anymore. So we still have all of our numbers, all of our calculations set up. And if we need to find a different product, we can make those changes right in there and see if anything else has to be done elsewhere in our budget. Okay, so these are just a few select cost-saving tips, but the first one, and again, I hope this has been clear, is that using error budgets can help you save cost. Remember, we've got this multidisciplinary view of things, so we're not going to spend a lot of time trying to get $2 out of one area when we could be getting $10 out of another area. Use a lens design that has low sensitivities. In a way, that's a different course, but it is important, like I said, that the lens designer has the ability to be doing the design in parallel with all this other stuff that's going on, because sometimes we're going to need to change those sensitivities. There's a polynomial in an SPIE paper called the cost of tolerancing. That polynomial gives you a relative sense of how your cost changes when you change certain tolerances. It's pretty neat. Another idea is to find out how all tolerances will be verified. So I alluded to this a little bit about metrology, but to get a really good sense of, for every one of those numbers in our budget, how is someone in your company or someone outside of your company going to verify that tolerance? That can be very eye-opening. Okay, you may be that measurement uncertainty may be 10% of the tolerance itself, and you're going to feel really good about that. But if you can't find out how it's going to be verified, or you're uncertain about how it's going to be verified, you're going to want to pay a little more attention to that element, possibly loosen the tolerance, etc. Making non-recurring versus recurring cost trades. So let's say you have this recurring A sphere that's very, very hard to make. That's going to cost you a lot of money for every optical system that you make. You might want to trade that with some non-recurring efforts, like coming up with a new way to test the system or a new compensation plan. And then finally, I actually just thought of this one this week while I was preparing for today. I thought it might be kind of neat to tag different areas in your budget tree with these little green dollar signs and these 3 red dollar signs. So it is also instantly obvious when people look at the different parts of the system, or the different stages of development, where we're doing really well with cost and where we're hurting with cost. Again, people will see those, they'll talk to each other, they'll help each other out, they'll make trades. So this all leads to a really nice view so that we can even out the pain in terms of technical achievement, as well as the pain in terms of cost. So in summary, thank you very, very much for coming. I hope to see some of you in the future. And I just want to leave you with this very famous quote, that creating error budgets provides a comprehensive framework for keeping track of requirements and sub-requirements. Error budgets provide a method of clearly sharing data so that multidisciplinary team members are up to date and can share excellent ideas. And again, here is my contact information. Please feel free to shoot me questions if you have them in the near future. And with that, we will go to question and answer.
Thanks so much, Jennifer, for that excellent presentation. I actually really enjoyed listening to it, especially about how certain personalities are well suited for this type of work. And then I also noticed in one of your slides, you said that to consult optimists and pessimists, which I've never heard before, but I think that is a fantastic suggestion all around. So much great information here, and clearly there's going to be so much more information in your full day course. And this is just the tip of the iceberg and an overview. We're going to go into the question and answer session now. And get through as many in the scheduled time. Again, a reminder, if you have a question, it's a great opportunity to ask Jennifer, and please put your question in the Q&A box. It's on the bottom of your screen there. It'll say Q&A. So let's see. The first question we have here is from Adrian Tikint. I apologize for any mispronunciations of names. Adrian, if you'd like to unmute your mic and ask Jennifer your question.
Hello, thank you for giving me the opportunity to ask the question. I was wondering at step 7, what tool do you advise to analyze the actual tolerances during shipping?
Were you able to catch that, Jennifer?
Yeah, so I think it would be some kind of finite element modeling tool. Is that address sort of what you're thinking about?
Yeah, okay. I never
Okay.
did that before. I've never done that before. So indeed, I would also think go in that direction.
Okay, great. Yeah, I think it'd be finite element modeling or any SolidWorks, any program in which you could assign forces as loads. I'm by no means a mechanical engineer. You could also actually build one and drop it, right? So you could actually do this fact finding using a real system.
Yeah, great idea. Okay, cool. Thanks.
Yeah.
Great, thank you, Adrian. We have another question here from Victor Tun. If you'd like to unmute your mic, I think you have permission to unmute at this point. Hi, Victor.
Hello. Great presentation. My question is on step 8, the Monte Carlo simulations. If you're not an optical designer, but you're going through this process, you don't have Zmax, are there alternative software packages that use like Excel or something like that to work out the statistical?
That's a very, very good question. I have either used Code 5, Zmax, or I've actually written my own scripts to do this. And it's really not as hard. I'm really not a very good programmer, but specifically when you have distributions that are not normal, or not available in the lens design codes. So they might have a top hat function. I'm not quite sure what they all are, but if you have a distribution that is not included, then you're really going to have to write your own script for that. But like I said, I've done that. And once you go through and set up you ask the script to choose a value between 2 bounds according to a certain distribution for each and every tolerance that you have, then you just put a loop around it and run it 100 times or run it 10,000 times. And then, yes, I've actually written my own scripts to actually take the resulting data and to bend it in a way that I can create something like this plot here. If anybody knows the answer to this question, Victor, if they could put it in the chat, because I have not found a program that does that. I've actually just written it myself.
Oh, it's a different type of program, right? Just, yeah, do it yourself. Yeah, but thank you.
Yep. Just like write in Python or MATLAB or something. Yeah.
Thanks, Victor. There is a question from an anonymous attendee asking if there are some templates for error budgeting that you could recommend or share.
That is not something I have found either. I would be happy to share mine. But they're not written for the general public, but I do share mine with students when they ask for them. So I can just give you examples. Mine are all in spreadsheets. And the math to hook up to do that flow and to hook things up is all buried in there. But no, I don't know of any commercial software that does this.
Thanks, Jennifer. It looks like there's a question here in the chat from Luis Jose. Sorry, I can't see the entire name in the chat about Monte Carlo simulation. Luis, I don't know if you want to unmute your mic to ask your question. I'm happy to read it as well. Ahead and read it aloud. If you are able to unmute your mic, please feel free to come on. The question is, once I was told that the Monte Carlo simulation has to be treated different from when you plan to manufacture/build 1 or 2 units and hundreds, and just your thoughts on that.
Oh, I have thoughts on that. Yes. Yeah, back in the 80s when I was young, we had this manager who didn't believe in Monte Carlo, which I thought is funny because Monte Carlo it's simply a mathematical procedure that collects data for you, given various combinations of tolerances, right? So it's not like the tooth fairy. It is a procedure. I do resonate with the idea that if you're only making 1 or 2, you might, and that's how I started my career, you might want to be very, very careful about using the data like we see here, this bell curve, because every once in a while there will be an optical system that falls outside of those bounds. So you have to be very, very careful. However, the chances of building a system, let's go back to the 83% chance that I said, given a set of tolerances and distributions, if you are truly using the correct distributions and the correct tolerances, this will tell you the chances of that optical system being in specification. So you may be only making 1 or 2. So we could say that 83 out of 100 should be in spec, or you can say that for model number 1, there's an 83% chance that that will be in spec. So again, I do recommend using both methods.